Hi everyone, this video is the solution for example 3 on the topic of beam deflection. So we're still doing a cantilever, but now we're going to do with a UDL and a UDL that doesn't go all the way to the end of the beam. So similar as before, we're going to start by defining our axis. So our Z axis is going to go from left to right, and the first thing we need to do is write some sort of moment equation. So the first thing you have to understand here is the moment for this case should be parabolic because it's a UDL, so we should expect some sort of z square function. Now, how do we get this z square function? So imagine we're trying to get the moment here at this position. I'm just going to cut the bar over there, and this will be our UDL, and that will be our red dot here. So what would be the moment caused by the UDL of 24 in that red dot? The first thing we would do is calculate the total force, which is 24 times z. So this total force here is 24 times z. Again, z is nothing more than the distance between the tip of the beam and that red dot that is a generic point. So 24 times z gives me the force. So what would give me the moment here that would give me that reaction is 24 times z, that's our force, and now the distance is nothing more than z divided by 2. So times z, all of this divided by 2. And here you can see straight away our z square parabolic function. In this case, it will be 12z squared, or you can write it 24z squared divided by 2. So we already solved the problem of the parabolic moment, so we could write straight away that this is minus 12z squared, and we would be done. But now there's a little problem, is after a certain point, let's say here when we get to that green dot, the load stops. So what's the trick here? The trick is to assume the load is going to go all the way until the end. So if the load went all the way until the end, we could write that the moment is nothing more than minus 12z squared, and that we would be done. But what we're going to do is assume the load goes until the end, and then we're going to add another load that cancels it. So this black load and the red is with a minus sign because it's causing tension on the top, so it makes a sagging beam. But the green one would be a hogging moment, right? It will make the beam do something like this. It will be a happy beam. So what we're basically going to do now is add 12z squared. But now what's the secret? The effect of the green loads only starts when z is greater than 4. So what we're going to do here is similar to what we've done in example 2, is substitute z with z minus 4 squared, which is an example of a Markowitz function. So long story short, we have our z squared that we derive here on the bottom, but this minus 12z squared assumes the load goes all the way to the end. So we let that be the case, but since we want to cancel that red load that is not there, that is fictitious, we add this green one, and therefore we can cancel them out. So this would be our equation for moments. So yet again, once we get to this equation, the problems are exactly the same as before. So if we have that as our moment function, we can write our curvature function. So y double dash of z is minus m divided by ei. So this will be equal to 1 over ei. So then we're just going to change the signs. Plus 12z squared minus 12 z minus 4 squared. And then we're going to do our first integration. So rotations is the integral of curvatures, dz, and that is equal to 1 over ei. So now, when we integrate this, we're going to get cube and divide by 3. So we get 4z cubed minus 4z minus 4 cubed plus c. And now our deflection is the integral of our rotations, again dz, so y dash z dz. So we're going to do 1 over ei and integrate this expression before. So this will go to z4 and divide by 4. So this is just z4 minus z minus 4 cubed plus cz plus d. Finally, we get our c and we get our d by using the boundary conditions. So we're going to find out the boundary conditions are, as the previous case, on the right side. So we get that the deflection and the rotation when z equals 6 are equal to 0. So rotation when z equals 6 is 0, and the deflection when z equals 6 is also 0. So this is our boundary conditions. Okay, so now we can get that the rotation when z equals 6 is 0. We're going to take this equation here, this one here on the top, to find c. So we get 1 over EI times, and now it's 4 times 6 cubed minus 4. And this will be z minus 4, so it's just 2 cubed plus c, and we know this has to be equal to 0. So what we get here is that c is going to be equal to, so we're going to do in the calculator first. So here we get 832, so it goes to the other side, becomes minus 832. Okay, so we found c. Now to find d, we're going to take the other equation and replace z with 6. So we get 1 over EI times 6 to the power 4 minus 2 to the power 4 minus 832 times 6 plus d. And this has to be equal to 0. Therefore, we can calculate d. And again, take the calculator. And here we get minus 3712 goes to the other side, becomes 3712. So now when we have our c and d, our integration constants, we can write our y of z, and that's equal to 1 over EI times z to the power of 4 minus z minus 4 to the power of 3 minus 832 times z plus 3712. And here, if you're interested in the deflection when z equals 0, so similar to the previous exercises, the maximum deflection in this problem is always at the tip. So when z equals 0, again, all of this simplifies except the 3712, and the 1 over EI stays there as well. So this exercise mainly helps you deal with UDLs. Expect a quadratic function in the moments, and because you integrate, you get a cubic function in the rotations and then a quartic function in the deflections. Okay, so thank you for watching and have a nice day.